Okay, so good day everyone. My name is Ian Gabriel Dizon from BACE 3G, and this is for dynamics of rigid bodies. Now we're going to discuss example number 1 from relative acceleration. So let's begin. The wheel of radius r rolls to the left without slipping, and at the instant considered, the center O has a velocity v sub 0 and an acceleration a sub 0 to the left. Determine the acceleration of points A and C on the wheel for the instant considered. So, we have our figure here. This is point 0, this is point C, and this is point A. We have a angular velocity and acceleration rotating to the left direction. We also have a sub 0 and v sub 0, which is the initial velocity and acceleration, and the radius. We also have a angle theta and r sub 0 from point A. Now, we don't have any specific numbers given, meaning the final answer that we are going to obtain are just variables or equations. So the formula that we are going to use are the ones that we also used from the previous videos, which is the angular velocity is equal to v sub 0 over r, and the angular acceleration is equal to a sub 0 over r. Now, we are first going to solve for the point A. So, the acceleration for point A is equal to a sub 0 plus acceleration to A and O. This will equal to a sub 0 plus acceleration of A and O normal plus acceleration of A and O tangential. Now, we're going to solve for the values of normal and tangential. For the normal, acceleration of A, O, normal, we have r sub 0 multiplied by the angular velocity, now squared. Now we have a equation for the angular velocity, which is W is equal to V sub 0 over R. So we are going to substitute that. We are going to have R sub 0 multiplied by V sub 0 over R. Next one is for the tangential. We have acceleration A and O tangential is equal to R sub O multiplied by the angular acceleration. Also, we have a equation for the angular acceleration, so we're just going to substitute it. Is equal to r sub 0 multiplied by the a sub 0 over r. Now that we have that, we can use vector addition in order to solve acceleration for point A. So we're just going to illustrate first. Let's say this is point 0, and then this is okay, then say this is acceleration point a sub 0, then we have the normal acceleration of A and O normal, and then the tangential at a perpendicular direction from the normal, because it is the because the tangential is perpendicular to the normal. So let's say the direction, that meaning this is 90 degrees. This will be the acceleration of A and O tangential. Okay, and then this is the acceleration at point A. For us to solve the acceleration at point A, we're going to use the Pythagorean's theorem, which is A acceleration at point A is equal to square root of acceleration point A normal squared plus acceleration A sub A tangential squared. Now we are going to solve for these two. For the normal, acceleration A normal is equal to A sub 0 cosine theta plus acceleration point A and O normal. For the tangential, acceleration at A tangential is equal to A sub 0 sine theta plus acceleration at point A and O tangential. Now that we have the value for these two, we can substitute it here, and then we will have the equation. So let's just write here the acceleration for A is equal to okay, A sub O cosine theta plus acceleration at A and O normal squared plus A sub O sine theta plus acceleration at A and O tangential squared. So this is our answer for acceleration at point A. Now we can also use we can also substitute angular acceleration, but it's only optional. It's not really required, but I can just show it to you. So if we are going to use angular acceleration, then acceleration at point A is equal to square root r multiplied by the angular acceleration cosine theta plus r sub O multiplied by omega squared plus r multiplied by the angular acceleration sine theta plus r sub 0 multiplied by the angular acceleration squared. So this is the equation will be if we're going to use angular acceleration, but let's just use this one. Now let's solve for acceleration at point C. for acceleration at point C, we have AC is equal to A sub O plus acceleration at C and O. Now we're going to solve for the normal and tangential of acceleration at point C at O. So A, C, and O normal is equal to R radius multiplied by the angular velocity squared, which is directed from C to O. For the tangential, we have acceleration of C and O tangential is equal to R multiplied by the angular acceleration, which is directed to the right. Solving this, we will have a final answer for acceleration at point C is equal to R multiplied by omega squared. This is the acceleration at point C. So that is our final answers for example number 1 in relative acceleration.